So at the end of lecture 3, we had some nice solutions to the wave equation, and we had them in form of these unknown coefficients, right? And we said, well, to get those, to get some more detail in there, to know those coefficients, we need to have some more constraints in our problem. And we talked about how the ocean provides these boundary conditions that are going to provide those constraints mathematically. So today, we're going to talk about how we deal with interfaces, the surface, the bottom, and we're going to talk about reflections and an interface. So let's draw our interface, a line, that's it. And let's draw our incoming wave. It's got some wave number k, some angle theta, and there's going to be some reflection with an outgoing wave number k prime and an outgoing angle theta prime. And you're going to have two media here. Media 1, media 2, okay? In each one, we're going to have a rho 1, C1, rho 2, C2, density and sound speed, respectively. And a coordinate system will say this is going to be Z here, this is going to be X, okay? And we're talking about plane waves, okay? So our problem stated here is a plane wave incident on horizontal stratification. Okay, so how do we write that down mathematically? Well, we can have our incident pressure field simply written as E to the I K dot X, right? And the reflected plane wave that we'll say is called PR. So reflected, and this will be incident, I guess. We should write that down. Be specific. PR is going to have some coefficient R out in front, which we're going to call the reflection coefficient at some point. E to the I K prime dot X, okay? Now, we're warming up. Let's get everything on the same page here. X, we're just talking about two-dimensional, X and Z. K, we're just talking about KX, KZ, right? And if we want to write those in terms of our nice angles, theta and theta prime, we're going to say this is going to be K sine theta minus K cos theta, and then for K prime, that's going to be K prime sine theta prime, K prime, cos theta prime. Okay? So the total pressure field in region 1. Well, we can simply write down that the pressure field is given by the incident plane wave and the reflected plane wave. Oops. That's not great. Okay. Okay. And of course, remember we had these handy relationship. We said K is equal to the norm of K, and actually we know that it's equals K prime. Why? Because this is equal to omega over C, or 2 pi F over C. And since C1 is the same everywhere in region 1, we know that K will be the same everywhere in region 1 as well, because the frequency is fixed. Okay? Makes sense? And so what is R? R is the amplitude of the reflected plane wave right? So we're going to define it as the plane wave reflection coefficient, okay? Okay, what else can we infer about this problem? Well, going back to this little important thing here, we can also say that lambda is equal to lambda prime by continuity. So the wavelength, because of the frequency, well, by continuity, the frequency and the wavelength must be the same everywhere in region 1 because the sound speed is the same everywhere in region 1. And so that allows us to infer that theta is equal to theta prime. Okay, this is a, classic thing we know about optics as well, so it's very intuitive. This is the angle of incidence. This is the angle of reflection, and they must be the same. So, oops. Really have trouble getting to the next page for some reason on this thing. Okay. So by definition now, we know that R, we can define R as having some amplitude part, right? Oops. Amplitude response and some phase response, right? And we can say that's going to be equal to PRX, PIX at Z equals 0, so at the interface. So if you remember from lecture 4, we talked about, soft and a hard interface and some of the fundamental physical laws that we expect, right? And how those define our boundary conditions about the velocity in the Z direction, for example, in this case, or the pressure going to 0 in the soft case. So, for example, let's talk about the pressure release surface in this new framework. Pressure release surface, P goes to 0 as Z goes to 0. And this is, I think we called this soft in our previous lecture. So if we go back to our just expressing the pressure field at Z equals 0, so at Z equals 0, on the left-hand side we're going to have 0 for the total pressure field, and then we have e to the I k x sine theta plus r e to the I k x sine theta. Now we've said k prime equals k, and so this works out very quickly. R equals -1. Okay, and so this is super important little result. It's basically telling you that if the pressure goes to 0 at the interface, that you have a perfectly reflecting mirror. Essentially, you have an acoustical mirror where the sign of the amplitude is switched, right? Okay, so we better write that down just to keep it, hard in our memory. A wave reflects off the surface by flipping its sign amplitude. Okay. So, what was the other simple little case that we looked at? Okay. That was the hard case. And that was where the derivative of the pressure or the velocity goes to 0, right? So you have an interface where the impinging sound pressure fluctuation just can't move the interface at all. So you need that velocity to go to 0 so there's finite force across the interface, right? Got to respect F equals ma. Okay. at z equals 0, we're going to have dp, and this time, you know, we had it written in terms of dp dn, but really this is dp dz because that we're talking about a horizontal interface in our little diagram from page 1. Oops, writing that all out again. Equals 0. Okay. So if we calculate that, we're going to have dz p is equal to minus I k cos theta e to the I kx sine theta plus I k r cos theta e to the I kx sine theta. Wish I bought a bigger iPad already. Damn. So we can solve that, right? This is equal to 0. And so we get r is equal to 1. Okay? Here the phase is unchanged. Slash the amplitude is the same. Right? So no flipping of the amplitude or no changing of the phase. And the most interesting thing about both of these cases, no energy is transmitted to region 2. So very, very, very simple cases here, but very applicable to the ocean. Very applicable to the ocean. Now let's imagine something in between, okay? Something in between hard and soft. Man, there we go. Wow, it did it. Okay, and we're going to call this a fluid-fluid interface. Fluid. And just for imagination's sake, that soft interface from before, really that's like a fluid air or a fluid vacuum interface. That hard is like a fluid bedrock, you know, like it's somewhat practical. A fluid steel interface, you know, you can imagine lots of things which are hard that are pretty close to what's actually in the ocean. So that's why I'm saying, hey, we basically did high school math and came up with something that's pretty applicable to acoustical oceanography. So let's redraw this little diagram we had here. We've got our incident wave. We're going to call this K1. We have K1 prime. We have theta 1. We're going to have theta 1. We know those are equal now. And now we're going to have, well, I should maybe make it look a little different, let's say. Theta 2. We're going to have rho 1, C1, rho 2, C2. This is going to have wave number K2. And we're going to say this is region 1, region 2. Okay? Best part of any problem is making the little diagram at the beginning. So we know our pressure field in region 1 already. So let's just say, what is our pressure field in region 2? In region 2, well, we're going to have an e to the I k2 x sine theta 2 z cos theta 2. Right, so I've already multiplied out x and, already multiplied out k dot x here. But I'm missing something here, right? We need to say something about how much energy is going across. So we're going to use T. Can you guess what T stands for? Transmission coefficient. I know you guys were all yelling that out. Your roommates are like poking their heads in the door. What the hell are you talking about? Yeah, transmission coefficient. Okay. So we need a boundary condition across this interface now, right? BC. Well, since the first time, I better write the whole thing out. Boundary condition BC. So we go back to our intuitive fluid mechanics, physics brain, and we say, okay, well, first of all, we know that pressure in region 1 at the interface, it's got to be equal to the pressure in region 2. Oops. Got to be equal to pressure region 2 at the interface. And that's pressure continuity. That's this idea. We already talked about this a little bit, but you know, what is pressure? It's force per unit area right at this interface. If you have some sort of delta F, some sort of, you know, finite difference in force, you're going to be tearing apart the interface because you're going to have your matter accelerating differently at in the different regions, right? So, okay, I might as well write that down. Let's see. Must not have a finite force differential across an infinitesimal great, my bad spelling hidden by my bad handwriting. And the reason is here, if we have a finite delta F, then we're going to have an infinite acceleration to make up for that. Okay, so that's your first boundary condition. Wow. Okay. So the other thing we talked about was, of course, with a hard boundary condition, this idea that, you know, if you had something infinitely hard, the velocity, you know, the vertical velocity would have to go to 0 because there's just nowhere for the particles to go. Okay. And we can say the same thing for this fluid interface, except we're going to say that, except here we're going to say that the vertical velocity in region 1 must be equal to the vertical velocity in region 2. So a slightly more sophisticated version of the same thing, basically that your interfaces have to move in total harmony, in total synchronicity, in order to not to violate the same idea of the finite force across an infinitesimal distance. Okay, so now the game is sub in P1 and P2, right? We have the P2 expression over here. P1's from a few pages back. Sub in P1 and P2 into BCs. We're just playing the same games that we always play, right? Okay, so when we do that, 1 gives us, we get 1 plus r e to the I kx sine theta 1 equals t e to the I k2 x sine theta 2, right? And we can just do nice simplification. Let's put all our exponentials in one side. And so now we have k2 sine sine theta 2 minus k1 sine theta 1. Whoops, put the 1 in there. Okay, and of course we've gotten rid of the kx altogether. It's canceled out on both sides. And okay, so now where do we go? How do we simplify this even more? And I'm going to say now, now seems like a good time for ... I know, again, you're screaming this out. You're like, man, we have sine theta 2, we have sine theta 1. Let's get some relationship between these guys. And that, of course, would be Snell's law. Okay? So, what did we have for Snell's law? Well, we had that K1 sine theta 1 is equal to K2 sine theta 2. And that, of course, you know, I think we wrote maybe before that sine theta over C was constant, right? K equals omega over C, K1 sine theta 1 over omega equals K2 sine theta 2 over omega, right? So that's how we get that. Okay, so let's plug this in. Plug into our equation. And what do we get? Well, very simple. We get T equals 1 plus R. Wow. So what does this look like to you? What are we really saying with this equation? Well, basically, this is just almost obviously intuitive, right? Of course, 1 plus the reflection equals the transmission. It's conservation of energy, right? Okay, so what else? What can we do next? Well, now we're going to use 2. Well, we're going to have minus I K1 cos theta 1. So we're just plugging in our P1 and our P2 into boundary condition 2. 1 minus R. We have an e to the I K1x sine theta 1. Then we're going to have an minus I t over rho 2 cos theta 2 e to the I K2 x sine theta 2. Now, again, you're saying we got to use Snell's law. Start plugging some stuff in. We can do some crossing out right away. Actually, you know what? I've always wanted to do to cross things out in a different color, and I just never have the chalk for it. So now I'm going to use this electronic thing to cross things out. What happens when we put in Snell's law? Boom. We get rid of these altogether, and I'll say by Snell's law, right? And so this simplifies quite a bit. What does this simplify to? Well, what's left over? We're going to have a 1 minus R cos theta 1. And then I'm going to say we're going to have n over m here. And then we have our t cos theta 2. What's an n and m? Where n is equal to the ratio of the wave numbers in the two different regions, or you could say, of course, the ratio of the sound speeds, right? And m is the ratio of the densities. So you really see how this concept of impedance, right, is super important. You need to know about sound speed, you need to know about the densities to understand reflection and transmission. So n is an index of refraction. Or at least it's analogous to that index of refraction, right? We had with optics, index of refraction, of course, was the sound speed, or sorry, the speed of light in the material versus the speed of light or over the speed of light in a vacuum, right? So here, since we don't have that sort of absolute speed of sound, we have the relative index of refraction. So the speed of sound in one region versus another, okay? Not quite as clean, but Very analogous. Okay, so let's go to a new page. So let's combine line 1 and 2. Oops. With Snell's law and get a much more general expression. Now we're just going to say for R, right? Because we had expressions for T and R. We have two equations. Let's solve those two equations and get something more general. So we had R. It turns into M cos 1 minus N cos 2 all over M cos 1 plus N cos 2. And we can simplify that even further, so it's all in terms of theta 1. Now we have N squared minus so this gives us a reflection coefficient, all in terms of these, this index of refraction, ratio of densities, and the incident angle. Okay. This is super useful, of course, because if we're in the ocean trying to measure something on the bottom, well, we don't really want to go into the bottom to measure the angle of transmission, right? It'd be a little bit difficult. So we can do everything from the side of region 1. Of course, we can write this in terms of impedances. Well, we could use a little help with that symbol. 1 where psi is equal to pressure over velocity normal. And so really, there's lots of analogies here to electric circuits and optics. I'm sure these things are quite familiar, but really useful expression. Now, what happens at normal incidence? Well, obviously, we get some cosines going to 1 and some sines going to 0. We can actually simplify things even further. I'm going to write our m's and n's in terms of rhos and c's. Right? So it really is just the properties, right? Just the properties in the two different regions give you that reflection coefficient. So let's write that down. This is, just a very, very elegant, simple solution. Magnitude and phase of R depend on relative properties. C1, C2, rho 1, rho 2. That's it. And the whole motivation here is useful if we consider the bottom as a fluid. Is the bottom a fluid? Sort of. Right? No, it's not. It has shear waves. It's definitely not a fluid. But how close can we get? Well, that's something we'll talk about a little bit more. Let's go back to reality for a second. Back to reality. Okay, what does the bottom actually look like? Right? Let's ask ourselves this question here. So we know it supports shear waves. That makes it non-fluid-like. At the same time, it's a mixed. It's a mixture of grains. It's fluid in between. So it's let's look at the interface in terms of these fundamental density and sound speed. So water, okay, density of water, seawater, we like to say 1024, let's say 1,000. Fresh water, this is in kilograms per meter cubed, or you can say 1 gram per centimeters cubed. Wow, what a beautiful metric system it is. And sound speed in seawater is about 1,500 meters a second. Okay, so we can have different types of bottom, right? Fluid type bottoms. I'm not going to say case. I'm going to say case A. Case A. So the density in the bottom is greater than density in the water column, and the sound speed in the bottom is less than sound speed in the water. And that translates to M greater than 1, N greater than 1. Okay? And I'm just going to say in parentheses here, typical silty clay, aka mud, these are true. Okay, so the density in mud, I'll say it's about 1.5 grams per centimeter cubed, and then sound speed in mud is, well, it can be 1475, let's say. Very approximately here, but in general, sound speed in mud is less than in water. Density is more. Okay? So R theta 1, right? When N is greater than 1, M is greater than 1, and M is greater than N, then we know that we have some sort of 0, right? Goes to 0 at, I'm going to call it theta B. And from optics, you probably know this is called Brewster's angle. The B is not just for bottom here. So we can solve that, right? We can solve that equation very quickly. We get this sine over this nice ratio of m squared minus n squared, m squared minus 1. And what does that look like if we draw a little figure here where on the y-axis I'm going to have magnitude of the reflection coefficient, and I'm going to have angle on the x-axis. Well, it's easy to see what the value is here at theta equals 0, and we're going to go out to, we have, if you look back at the expression, m minus n, n plus n, right? We already said that's the incident angle. We know that we're going to have some theta b here. It's going to decrease monotonically, theta b. And then what happens as you go all the way out, 90 degrees, you go up to pi here. Okay, well, pretty good. Now, what about the phase? So let's make these one of these double y-axis plots, okay? Well, the phase, right, everything's going to be real below the Brewster's angle. So the phase, actually, you know what? Wow, I'm going to make the most of the technology. Phase, it's in red. So the phase stays 0. Now, all of a sudden, we have a imaginary component, just goes up to pi. There you go. Quite simple. Okay. All from that simple expression. I think I need a new page. Yeah. Okay, so let's go to case 2 now. So we had the muddy case. The muddy case where the density is higher, the sound speed's lower. Case 2, I'm going to call it case B. Now we're going to say density's higher, and sound speed in the bottom is higher. Okay, fast bottom. Typical values for sandy sediments, let's say it's going to be 1.8, 1.7 grams per centimeter cubed. And typical value for the bottom sound speed might be something like 1,800 meters a second, 1,700. So this is sandy bottom. So now this means that n is less than 1, m is greater than 1. And in this case, instead of Brewster's angle, right, instead of that expression going to 0, we can see that there's something funny happens here at a critical angle. I'm going to call this critical incident angle theta prime I. And we'll just talk about this in terms of a Snell's law perspective. You know, from our original diagram, we had some incident angle here, and we have some transmission angle here. You see the transmission angle grows. So there's going to be a certain critical incident angle, which is larger, right? Goes this way as your ray becomes, I guess you could say, shallower, where the transmission angle is actually going to be parallel to the interface here, okay? So at theta prime I, the critical angle, theta prime t goes to 0. Or I guess I should say pi by 2. So when did this happen? Well, it's quite easy to see. This is when we have this expression. And just because of Snell's law again, right? We just put in when does that condition happen, and sure enough, you can solve that equation quite simply and get this expression for the conditions under which you have what's called total internal reflection, right? Well, at least right at the beginning of total internal reflection. Okay, so theta I, transmitted wave is parallel to interface, okay? And this is what we call total internal reflection. You know, it's good to think everything we've written down holds true for plane waves. They don't have to be acoustic plane waves, it could be optics, and of course this is what's exploited for fiber optic cables, right? So you have total internal reflection in a fiber optic cable. You never have any energy transmitted into region 2, into the glass of the optical cable. So similarly in the ocean, we can have a waveguide where there's never any energy transmitted into the bottom of the ocean as long as we are past this critical angle. It's a very powerful, simple idea, right? So we go back to our expression. So P1, let's say in region 1, P1 in terms of x and z equal to 2 dix sine critical angle cos kz. Okay? And in the bottom, P2 in region 2, P2 is equal to, well, being sloppy here, xz is equal to t e to the I k2 x sine theta 2 minus z cos theta 2. And we want to evaluate that at theta 2 equals pi over 2. Well, that simplifies things significantly. And we want to say that it's equal to 2e to the I kx. Okay? So really we have an interface wave traveling along the boundary. Sometimes it's called the refracted arrival. Okay? Interface wave. Why would you call it the refracted arrival? Well, the interesting thing here is if you remember back up to here, we have a very fast sound speed in the bottom, right? Faster than the water. Water's 1500. So you can imagine if you have your receiver here, you have your source here, surface, you might have, actually let's make, let's make our source close to the bottom, just to make our point a little more clear. Here's our source, broadcasting out as plane wave. You might have one path that goes directly to the receiver. The sound speed along that path is 1500 meters a second. You'll have some other path which goes into the bottom, provided the bottom has the right, the right density and sound speed. You're actually going to have a path that travels most of the way at 1800 meters a second, so it can arrive before the direct path, this refracted arrival. So that's pretty interesting. Okay. So now let's consider theta 1 is less than the critical angle. So R in our expression is real with zero phase, right? It's all real everywhere. When theta 1 is greater than the critical angle, we can rewrite R as m cos 1. And now we're just going to rearrange and take the imaginary part right outside of our square root, right? Which is really generating our phase term, right? The argument of the square root is real, then our phase term 0. Or sorry, if the argument of the square root is positive, our phase term 0. If it's negative, then we have to consider the phase, right? And so now we're going to say, well, it's always going to be positive, but we're bringing the I outside. Okay. Now everything in here is always positive. Okay? So, if we go back to, just writing this as a nice little imaginary number where this is all the real part, this is all the phase imaginary part here. Well, we can say that phase is equal to minus 2 inverse tan of sine squared theta 1 minus n squared all over m cos theta 1. Okay? And yeah, note here, magnitude of k incident is 1. So we can sub into the field and get, okay? Sub in to get field in region 1. So P1 now is 2 e to the I phi over 2 e to the I k times x times sine theta 1 cos k z cos theta 1 plus phi over 2. okay? If we combine with Snell's law, we can simplify our P2 to get 1 e to the I phi e to the I kx sine theta 1 and e to the kz square root of sine squared theta minus n squared. So we can see that there's a couple different components here, right? Here's just your regular propagating wave in S. In X, did I say S? And what is this component here? Well, there's no I, right? So it's not a plane wave. It's just a exponential decay in Z. So this is just a evanescent wave, what we call an evanescent wave. So, which means that its amplitude is exponentially decaying. In depth. So, this is a good example of an inhomogeneous plane wave, where it has two components. Propagating component and exponentially decaying evanescent component. We can detect both of these things, right? So it's kind of interesting in the sense that if you're close to the surface, you can detect this wave. Now, we want to draw the same picture we drew before for our case B. A little more room this time, where we have the amplitude, and we know it, amplitude of the reflection coefficient, 0. And we know that its starting point, right, it's going to be the same because it doesn't care about angle at all. But now we have, it's going to be increasing, right? Right up until that critical angle. So this will be 1 up here. So once you get past that critical angle, you have total internal reflection, okay? This is the total internal reflection region. Okay, and now we'll do the same thing we did before. We'll do 2 plots in 1, right? Here we're going to have 0 minus pi. And so now we have no imaginary part until we get to that critical angle, and then we have just a linear decrease down to negative pi. That's what our phase looks like. Oh, and I think I forgot to label this axis in terms of phi here. So all of this is to say that measuring R, which could mean the amplitude, but also the phase, is one very good way to infer the density of the bottom and the sound speed in the bottom. And the neat thing is that it can be done remotely, right? So we had all our expressions in terms of theta 1. So pretty basic. We basically used very basic physics, Snell's law, and this idea of plane waves at an interface that I'm sure you've seen before. All of that just to develop a pretty nice way of doing what's called our first an inversion problem. So this would be our first example of an inversion problem, where we want to go in the ocean, we want to figure out what's on the bottom, and we can do that by making some sound wave, in the water column, goes down, reflects off the bottom, comes back. We do that as a function of angle by moving our ship around or moving our source and receivers around. And we can learn something about what the bottom's made out of without having to go down there and grab a sample of it or take a picture of it or whatever. So that's our first sort of acoustical oceanography inversion problem. Dead simple and still used, very powerful, totally cutting edge. So I hope that was enjoyable.